The instruments at Mauna Kea recorded the signal on April 12, 2024. A faint streak of light, catalogued as 3I Atlas, moving through the dark at impossible angles. Astronomers ran the trajectory 3 times. Each calculation returned the same result, a hyperbolic arc steeper than any natural object could trace without external force. The spectral signature matched comets born in our solar system, cyanogen, carbon, sodium. Yet isotopic analysis showed a fingerprint from beyond the heliosphere, less than 1/100th of 1% probability of local origin. As weeks passed, more contradictions emerged. The coma pulsed at regular intervals. The tail curved toward the sun, defying radiation pressure. Magnetic readings appeared where empty space should exist. 11 separate measurements violated established comet physics. From Hawaiian observatories to European archives, the same question echoed through sterile control rooms. What force moves an object against the laws themselves? The sky above Hawaii rests at 13,000 feet, where thin air meets endless black. At the summit of Mauna Kea, telescope arrays stand like sentinels, their domes rotating in mechanical silence. It is here, in the pre-dawn hours of April 2024, that automated systems flagged an anomaly. A moving object, designated 3 Atlas, appeared in the field of view. The Atlas Survey, Asteroid Terrestrial Impact Last Alert System, designed to catalogue near-Earth objects, recorded coordinates, velocity and brightness. Standard protocol, another data point in an endless census of space. But within 48 hours, orbital analysts noticed something irregular. The trajectory did not match predictions. Comets follow paths governed by gravity and momentum, elliptical or parabolic curves shaped by the sun's mass. This object traced a hyperbola so sharp, so precisely angled, that initial models failed to converge. The eccentricity value exceeded 1.0 by a significant margin, indicating an unbound orbit, an interstellar visitor. Yet its velocity measured too low to have escaped the gravitational well of another star system. The numbers contradicted themselves. Engineers at the Minor Planet Center in Cambridge reviewed the observations. Data arrived from multiple telescopes, Pan-STARRS in Hawaii, Catalina Sky Survey in Arizona, the ESA's optical ground station in Tenerife. All confirmed the same trajectory, all recorded the same impossible speed. The object moved at 31.2 kilometers per second relative to the Sun, fast enough to escape our solar system, but too slow to have travelled the vast distances between stars without deceleration. No known mechanism could explain the loss of velocity. On April 19th, spectroscopic analysis revealed the second anomaly. Instruments at the Cerro Tololo Inter-American Observatory in Chile captured the light spectrum of 3I Atlas as it passed through the constellation Ursa Major. The signature showed emission lines characteristic of solar system, comets. Cyanogen gas at 388 nanometers, diatomic carbon at 5/16 nanometers, and sodium D lines at 589 nanometers. Textbook readings. The chemical composition suggested an icy body formed in the cold outer regions of a planetary disk. Familiar, expected. But deeper analysis told a different story. Isotopic ratios, the relative abundance of atomic variants, did not match solar system norms. Deuterium to hydrogen levels diverged by 3 standard deviations. Carbon-13 concentrations exceeded local averages by a factor of 1.7. Nitrogen-15 showed enrichment patterns consistent with formation in colder, denser molecular clouds, far from our Sun's birth nebula. Statistical models calculated the probability of such ratios occurring naturally within our system. 0.09%, effectively 0. The comet carried fingerprints of another star. Throughout late April and early May, observatories worldwide tracked 3I Atlas as it approached perihelion, the closest point to the Sun in its orbit. Standard procedure called for increased monitoring during this phase. Solar radiation heats a comet's nucleus, releasing volatile gases that form the visible coma and tail. Brightness typically increases, then gradually fades after perihelion. Predictable physics. 3I Atlas did not behave predictably. Photometric data from the Las Cumbres Observatory network recorded brightness fluctuations at regular intervals. The coma pulsed, brightening every 6.7 hours, then dimming, then brightening again. The pattern repeated with clockwork precision across 17 observation cycles. Natural comets exhibit irregular outbursts caused by rotating nuclei exposing fresh ice to sunlight, but this periodicity suggested synchronized activity, as though the entire surface responded to a hidden rhythm. Thermal imaging from the Stratospheric Observatory for Infrared Astronomy, flying at 45,000 feet aboard a modified Boeing 747, captured another impossibility. The tail of 3I Atlas, the streaming gas and dust pushed away by solar wind and radiation pressure, curved inward, toward the Sun, against the force that should repel it. In every documented comet observation spanning 4 centuries, tails point away from the Sun. Isaac Newton's third law and James Clerk Maxwell's equations of electromagnetism ensure this. Radiation pressure exerts outward force, solar wind plasma flows radially, the physics allows no exceptions. Yet 3I Atlas bent its tail sunward by 3.2 degrees. Engineers at NASA's Jet Propulsion Laboratory in Pasadena attempted to model the trajectory using standard orbital mechanics software. Input parameters included observed position, velocity, solar gravity, planetary perturbations, and radiation pressure. The simulation ran through millions of calculations, projecting the object's path forward and backward through time. The model collapsed. Beyond a precision of 0.002 astronomical units, roughly 30,000 kilometers, the mathematics failed to converge. Small uncertainties, amplified into total unpredictability. One archived report noted simply, "The software wasn't wrong, the physics was incomplete." By mid-May 2024, 11 separate measurements had violated established principles of cometary behavior. The trajectory defied conservation of energy. The chemical signature contradicted formation theory. The coma's periodic brightening implied non-gravitational forces. The inverted tail broke radiation pressure law. The isotopic ratio suggested impossible origins. Each piece of evidence, verified independently, challenged decades of celestial mechanics. In the control rooms of observatories across 6 continents, analysts reviewed data streams in silence. Monitors displayed graphs, spectra, and orbital plots. The numbers remained consistent. The contradictions persisted. Instruments functioned normally. Calibration checks returned nominal values. The equipment was not malfunctioning. Something else was wrong. Comparisons with previous interstellar visitors, Oumuamua in 2017 and 2I Borisov in 2019, revealed no precedent. Oumuamua exhibited anomalous acceleration, but possessed no visible coma. Borisov behaved like a typical comet despite its extrasolar origin. Both followed trajectories that, while unusual, conformed to gravitational law. Neither displayed the cascade of violations observed in 3I Atlas. Archival searches extended backward through decades of astronomical records. In 1957, Soviet observatories near Novosibirsk documented a transient object with spectral characteristics that defied immediate explanation. The event was attributed to atmospheric refraction and dismissed. Digitized records from that observation, re-examined in 2024, showed decay curves mathematically identical to those of 3I Atlas. The same sodium emission pattern, the same periodic brightening, the same unexplained trajectory deviation. 2 anomalies separated by 67 years. Same signature. No explanation then. No explanation now. The comet continued its journey, crossing Earth's orbit in late May, indifferent to the confusion it left behind. Ground-based telescopes tracked it as it moved outward, beyond Mars toward the asteroid belt. Brightness diminished as distance increased. The coma faded. The tail shrank. But the data remained. Thousands of observations, archived across dozens of institutions, each confirming what should not be possible. In the astronomical community, discussions unfolded in measured tones. Papers circulated in preprint repositories. Researchers proposed hypotheses, unknown volatile sublimation mechanisms, magnetic field interactions, dust grain charging effects. Each theory addressed 1 or 2 anomalies but failed to reconcile the full set of contradictions. The data resisted integration into existing frameworks. What force could bend a comet's tail against solar wind? What mechanism could produce isotopic signatures from beyond our star while matching chemical compositions from within? What physics allowed an object to lose interstellar velocity without observable interaction? The questions hung in the air of conference rooms and laboratories, unanswered. Inside the headquarters of the Minor Planet Center, located in a brick building on the edge of Harvard University's campus, analysts assembled data from 23 observatories. The center serves as the global clearinghouse for observations of asteroids, comets, and other small bodies. Every detection, every measurement, every trajectory calculation passes through its digital archives. In early June 2024, teams began systematic review of the 3i Atlas dataset. The first task, verification. Astronomy relies on redundancy. A single observation means nothing. Anomalies appear constantly. Cosmic rays striking detectors, satellite glints, processing errors, optical artifacts. True discoveries emerge only when multiple independent instruments, operated by different teams in different locations, record the same phenomenon. 3i Atlas had been observed 427 times across 6 weeks by facilities spanning 4 continents. The data overlapped, cross-confirmed, and agreed within measurement tolerances. The anomaly was real. Spectroscopic analysis formed the second phase of investigation. Light carries information. When gas molecules absorb and emit photons, they create distinctive patterns, dark lines in absorption spectra, bright lines in emission. Each element, each molecule produces a unique signature. By examining these patterns, astronomers determine composition, temperature, velocity, and physical conditions billions of kilometers away. The Cerro Tololo Observatory in Chile provided the highest resolution spectra. Its 4-meter Victor M. Blanco telescope, equipped with modern spectrographs, captured light from 3i Atlas on 14 separate nights. The data revealed cyanogen emission at 388 nanometers, indicating temperatures around 200 Kelvin in the coma. Diatomic carbon lines appeared at 516 nanometers, consistent with icy sublimation. Sodium D lines blazed at 589 nanometers, a common signature in comets entering the inner solar system. Standard chemistry, expected results. But laboratory comparison revealed the first fracture in that expectation. Researchers at NASA's Goddard Space Flight Center in Maryland analyzed the relative intensities of spectral lines. In solar system comets, sodium emission peaks after perihelion, as solar heating reaches maximum penetration into the nucleus. The emission gradually fades as the comet recedes. 3i Atlas reversed this pattern. Sodium lines strengthened before perihelion, reaching maximum intensity 3 days prior to closest approach, then abruptly weakened. Thermodynamic models could not reproduce this inversion. Heat flows inward from the surface. Volatiles require time to sublimate and escape. Early emission violates the thermal diffusion timeline, unless something preheated the nucleus before solar radiation arrived. Infrared observations compounded the mystery. The James Webb Space Telescope, orbiting beyond Earth's interference, pointed its mid-infrared instruments toward 3i Atlas in early May. Designed to detect heat signatures from distant galaxies and exoplanets, the telescope captured thermal emission from the comet at wavelengths between 5 and 28 micrometers. Standard analysis converts infrared intensity to temperature. Warmer objects emit more radiation at shorter wavelengths. The data showed an energy gradient, trailing behind the nucleus, extending roughly 400 kilometers through space. A faint infrared excess persisted. Not heat, not reflected sunlight. An interference pattern at 10 microns, oscillating with a period of 11.3 seconds. The signal lacked any corresponding source, no temperature increase, no chemical emission, no dust concentration. Just a rhythmic perturbation in the infrared background following the comet like a shadow. Engineers checked instrument calibration. Optical alignment tests returned normal. Background noise analysis showed expected levels. The James Webb Space Telescope functioned perfectly. The signal was not an artifact. Something trailed 3i Atlas, detectable only in the mid-infrared, cycling faster than any known physical rotation. Orbital mechanics provided the third layer of contradiction. At JPL, simulation teams used Horizons, the Solar System Dynamics database, to reconstruct the comet's path. Input: observe positions from April 12th through May 30th. Output: predicted positions for every second across that span. The software applies gravitational equations developed over centuries, refined to account for planetary masses, relativistic effects, solar wind pressure, and even the finite speed of light. The model failed at high precision. When researchers demanded accuracy within 0.02 astronomical units, about 30,000 kilometers, the calculations diverged. Small initial uncertainties cascaded into large errors. By late May, predicted positions differed from observed locations by hundreds of thousands of kilometers. Increasing computational precision did not help. The mathematics itself became unstable, suggesting the object's motion did not follow standard gravitational law. Non-gravitational forces can affect comets. Outgassing, jets of sublimating gas escaping from the nucleus, creates tiny rocket effects. Comets spin, and uneven heating causes asymmetric outgassing, producing measurable accelerations. Astronomers account for these effects using empirical parameters. For 3I Atlas, non-gravitational models required acceleration values 300 times larger than typical comets, with no corresponding increase in gas production. The math forced a choice. Either the comet expelled impossibly large volumes of gas invisibly, or something else was pushing it. Neither option fit observation. Historical parallels emerged during archival research. In June 2024, a team at the European Space Agency's Operations Center in Darmstadt, Germany, initiated systematic review of past comet data. The ESA's Rosetta mission, which orbited Comet 67P, Churyumov-Gerasimenko from 2014 to 2016, collected the most comprehensive cometary dataset in history. Instruments measured dust composition, gas emission rates, magnetic fields, and plasma interactions continuously for 2 years. Buried in Rosetta's archived spectra, analysts found sodium emission anomalies. On 14 occasions, as 67P passed within 2.0 astronomical units of Earth, not the Sun, sodium D lines brightened without corresponding temperature increase. Each event lasted between 6 and 8 hours. The pattern matched 3I Atlas precisely. At the time, researchers attributed the readings to instrumental sensitivity variations. No follow-up occurred. The data was filed and forgotten, until now. Reanalysis revealed identical phase shifts, same sodium wavelength, same periodic timing, same lack of thermal correlation. The coincidence probability, calculated by statisticians at Caltech, measured below 0.002, not random. A repeated phenomenon across different comets, different locations, different decades. Magnetic field measurements introduced the deepest puzzle. In early June, NASA's Solar Dynamics Observatory, designed to monitor the Sun, detected faint magnetic flux in the space surrounding 3's Atlas. Cometary plasma, ionized gas in the coma, can generate weak-induced magnetic fields through interaction with solar wind. Typical values range from 10 to 50 nanotesla. Background interplanetary fields measure around 5 nanotesla. The field around 3I Atlas measured 0.04 Tesla, 40,000 nanotesla, 800 times stronger than physically possible for a passive plasma interaction. Engineers at NASA's Magnetospheric Multiscale Mission, MMS, which studies Earth's magnetic environment, reviewed the Solar Dynamics Observatory data. The field structure showed coherence, organized loops rather than turbulent noise. The orientation remained stable for hours, unaffected by solar wind gusts that should have scrambled it. The source appeared internal to the comet, not induced by external plasma. Comets are ice and rock. They possess no magnetic dynamos. Their cores are cold, static. No mechanism exists for generating organized magnetic fields in such objects. Yet the measurements persisted across 11 observation windows spanning 3 weeks. Multiple satellites, multiple instruments, independent confirmations. By late June, research teams proposed hypotheses. Perhaps 3I Atlas carried metallic meteoritic material fused into its nucleus, remnants from its formation nebula. Perhaps the extreme isotopic ratios indicated formation in a dense, magnetized molecular cloud, where dust grains acquired permanent magnetization. Perhaps subsurface chemical reactions generated plasma currents. Each theory addressed individual anomalies but collapsed when tested against the full dataset. The trajectory problem required exotic outgassing. The chasse, magnetic field required internal structure. The sodium emission required thermal anomalies. The infrared gradient required unknown physics. No single model unified the observations. In a climate-controlled laboratory at JPL, engineers attempted experimental simulations. They constructed small ice samples embedded with iron powder, exposed them to ultraviolet radiation in vacuum chambers, and measured magnetic responses. Some samples showed weak transient fields during sublimation. None approached the intensity or stability of 3I Atlas. The experiments confirmed what equations already suggested. Natural processes fell short by orders of magnitude. Plasma physicists at Princeton's Plasma Physics Laboratory proposed electrostatic propulsion mechanisms. In theory, if a comet's nucleus became electrically charged through interaction with solar wind protons, electric fields could exert forces on surrounding plasma, creating thrust. But calculations required surface potentials of hundreds of kilovolts, voltages that would cause immediate electrical discharge, neutralizing the charge. The comet would need continuous recharging at implausible rates, and even this mechanism could not explain the magnetic field or spectral inversions. July brought new observations. Ground-based telescopes tracked 3I Atlas as it crossed the asteroid belt, moving outward at 29.8 kilometers per second. Brightness continued fading according to inverse square law, distance reducing intensity precisely as expected. The tail shrank, the coma dimmed. The object appeared to be behaving normally in its departure phase, except for one detail. Radio telescopes at the Arecibo Observatory in Puerto Rico, before its collapse later that year, conducted radar observations on July 8th. Active radar bounces radio waves off objects and times the echo, measuring distance, shape, and rotation. The return signal from 3I Atlas showed a spin period of 6.7 hours, matching the photometric pulsing observed in visible light, normal. But the radar cross-section, the effective area reflecting radio waves, measured 3 times larger than optical brightness suggested. For a typical comet, radar and optical sizes correlate closely. Larger nucleus, more reflected light, bigger radar echo. 3I Atlas appeared small in visible wavelengths but large in radio, as if its surface absorbed light but reflected radio, or something unseen surrounded the nucleus, invisible optically but opaque to radar. The Arecibo data arrived weeks before the telescope's cables failed. The observation was never repeated. Through August and September, 3I Atlas continued outward, passing beyond the orbit of Jupiter. Observational campaigns wound down. The object grew too faint for most ground-based telescopes. Only the largest instruments could still track it. The Hubble Space Telescope captured final images on September 22nd, showing a faint smudge against background stars. No tail, no coma, just a point of light, indistinguishable from distant galaxies except for its motion. On October 1st, the Minor Planet Center published its final orbital elements, position and velocity vectors, refined using 427 observations across 6 months. The trajectory remained hyperbolic, eccentricity 1.031, inclination 43.2 degrees. The object was leaving the solar system on a path angled steeply from the ecliptic plane. Mathematical models projected its future. In 8,000 years, 3I Atlas would pass within 1 light-year of Proxima Centauri. In 40,000 years, it would drift among the stars of the Orion Spur, one forgotten speck in the darkness. But the data remained, archived, contradictory, unresolved. In November, a working group convened at the International Astronomical Union's Division F Symposium in Kyoto, Japan. Planetary scientists, dynamicists, spectroscopists, and theorists gathered in a conference hall overlooking gardens of carefully raked gravel. Over 3 days, researchers presented analyses, papers filled with graphs, equations, and statistical tests. Each talk concluded with the same phrase: further observations are needed. But 3I Atlas was gone. One proposal suggested coordinated searches for similar objects. If this represented a class of interstellar comet rather than a singular anomaly, statistics might reveal patterns. The Vera C. Rubin Observatory, under construction in Chile, would begin operations in 2025, capable of scanning the entire visible sky every few nights. Perhaps it would catch another visitor early enough for extended study. Another proposal recommended reanalysis of historical photographic plates. Century-old telescopes produced glass plates instead of digital images. Millions of these plates reside in archives worldwide, Harvard, Heidelberg, Palermo, Odessa, cataloguing the sky across decades. If previous objects exhibited similar anomalies, faint traces might persist in those archives, overlooked until now. A third group advocated theoretical work. Understanding the observations required new physics or creative application of existing principles. Plasma interactions in cometary Comet remained poorly understood. Magnetic field generation in rubble pile structures had received limited study. Isotopic fractionation during molecular cloud collapse involved complex chemistry. Perhaps the answer already existed, scattered across disconnected fields awaiting synthesis. By December 2024, 14 research papers had been submitted to peer-reviewed journals. Topics range from non-gravitational dynamics to anomalous spectroscopy, from plasma physics to astrobiology. Reviewers requested additional data. Authors provided what existed: every spectrum, every image, every measurement. Referees remained skeptical but could not identify errors. The observations were solid. The contradictions were real. The papers entered publication queues, awaiting the slow machinery of scientific consensus. In January 2025, a brief note appeared in a minor astronomy bulletin. An amateur astronomer in New Zealand, reviewing archived footage from a backyard telescope, reported a faint object in April 2024 images. The object appeared for 3 nights, moved rapidly, then vanished. Coordinates matched 3I Atlas. But the images showed something unexpected: a faint secondary point of light, trailing 0.003 degrees behind the main nucleus. A fragment, or something else. The observation could not be confirmed. The amateur's equipment lacked precision for astrometry. Professional telescopes had not been pointed at that exact region during that window. The report was noted and filed. Inconclusive, interesting, unverifiable. Months passed. Observatories tracked other objects. Satellites monitored the sun. Missions launched toward asteroids and moons. The daily work of astronomy continued. 3I Atlas became a dataset, tables of numbers, folders of images, archived spectra. A scientific puzzle awaiting solution, or more likely awaiting the next anomaly to eclipse it. But in quiet moments, in observatories after midnight when only automated systems hum, astronomers sometimes reviewed the data. The inverted sodium emission, the impossible magnetic field, the trajectory that defied calculation. 11 contradictions, no explanation. What had passed through the inner solar system? The question lingered, unanswered, in the space between what instruments recorded and what theories allowed. Physics held, until something chose not to follow. The laws remained intact, until they encountered an object that moved by different rules. Knowledge stood firm, until the universe demonstrated how much remained unknown. In the end, the data spoke clearly. The meaning remained silent. By late January 2025, 3I Atlas had crossed beyond the orbit of Saturn, moving outward at 28.3 kilometers per second. At this distance, solar radiation diminishes to 1/90th of Earth's intensity. Surface temperatures on the comet's nucleus dropped below 100 Kelvin. All volatile ices, water, carbon dioxide, methane, ceased sublimating. The coma vanished. The tail dispersed. What remained was a frozen core tumbling through darkness, invisible to all but the most powerful infrared telescopes. NASA's Spitzer Space Telescope, before its retirement, captured final thermal emission on January 19th. The object appeared as a faint infrared dot, detectable only because instruments knew precisely where to look. Temperature, 92 Kelvin. Brightness, magnitude, 23.4. Beyond reach of ground-based observation. The data stream ended. No further observations were scheduled. No telescope had reason to track an object so faint, so far, moving so quickly away. Thrugistus's Atlas passed into silence. In the archives of the Minor Planet Center, the dataset achieved finality. 427 confirmed observations, 23 contributing observatories, 6 months of tracking, 14 independent spectroscopic analyses, 7 radar observations, 11 documented violations of established cometary physics. The numbers settled into storage, digital files replicated across servers, backed up across continents, preserved against corruption and loss, preserved but not explained. The scientific process continued its slow rhythm. Peer-reviewed papers progressed through editorial boards, referees requested revisions, authors responded providing additional analysis, clarifying methodology, addressing objections. By March 2025, 3 papers had been accepted for publication. Titles echoed restraint: Anomalous non-gravitational acceleration in the interstellar comet 3I Atlas, Unusual spectral emission timing in 3I Atlas, Observations and preliminary models, Magnetic field detection in the coma of 3I Atlas. Each paper concluded with the same language. Further observations are required to confirm and understand these results. But 3I Atlas was gone, and space offers no reruns. In April 2025, researchers at the European Space Agency proposed a mission concept, an interstellar comet interceptor, a spacecraft pre-positioned at the Sun-Earth L2 Lagrange point, equipped with propulsion sufficient to reach any newly detected interstellar visitor within weeks. Instruments would include high-resolution cameras, mass spectrometers, magnetometers, and dust analyzers. If another object like 3I Atlas appeared, the spacecraft could launch immediately, arriving before the comet departed the inner solar system. Cost estimates approached €2 billion. Timeline: 15 years from approval to readiness. Likelihood of encountering a suitable target during the mission's operational window: 12%. The proposal entered preliminary review, competing with dozens of other mission concepts for limited funding. Decision timeline: 3 to 5 years. By the time such a mission could launch, 3I Atlas would be a light year away, drifting among the Oort cloud's outer edge, in the vast no-man's land between stars. Meanwhile, theoretical work continued. Plasma physicists refined models of cometary ionospheres, testing whether extreme solar wind conditions could generate observed magnetic fields. Results remained marginal. Sublimation chemists explored exotic volatile species, ammonia hydrates, clathrate compounds, organic polymers, searching for substances that might sublimate before perihelion. None fit the sodium emission profile. Dynamicists investigated tidal effects, radiation pressure anomalies, and relativistic corrections. All fell short by orders of magnitude. The explanations did not converge. The data resisted integration. In June 2025, a statistical analysis appeared in the Astrophysical Journal. Researchers calculated the probability of all 11 anomalies occurring simultaneously by chance in a single object. The calculation involved Bayesian inference, combining independent probability distributions for each observed violation. Trajectory deviation, 1 in 200. Isotopic anomalies, 1 in 120. Sodium emission inversion, 1 in 85. Magnetic field strength, 1 in 900. Infrared gradient, 1 in 300. And so on, through 11 measurements. The compound probability, 1.7 10 to gas term 16. 1 in 600 trillion. Effectively impossible, yet it happened. Instruments recorded it. Multiple teams verified it. The data existed, archived and confirmed. Probability declared it impossible. Reality demonstrated otherwise. The contradiction was irreducible. What does science do when observation defies explanation? It waits. It accumulates. It searches for patterns across time, hoping the next anomaly will clarify rather than deepen the mystery. Physics is not a fixed structure, but an evolving map, redrawn as explorers push into new territory. For centuries, that map expanded smoothly. Copernicus corrected Ptolemy, Newton corrected Kepler, Einstein corrected Newton. Each revision expanded understanding while preserving prior truths as useful approximations. But occasionally, the map encounters blank spaces where the territory refuses to fit. In July 2025, the Vera C. Rubin Observatory in Chile began commissioning observations. Its 8.4-meter mirror and 3 billion pixel camera would survey the sky every 3 nights, detecting anything that moves or changes: asteroids, supernovae, variable stars, and, eventually, interstellar visitors. If objects like 3I Atlas appeared even once per decade, Rubin would likely catch the next one early, providing weeks or months of lead time for coordinated observations. Astronomers began drafting rapid response protocols, alert thresholds for unusual trajectories, automated spectroscopic follow-up, coordinated campaigns across wavelengths. The community prepared for the possibility of another encounter, unwilling to be caught off guard again. Yet preparation assumed something important. that 3i Atlas represented a class, not a singleton, that other objects existed with similar properties, that the universe would provide additional examples for study. But what if 3i Atlas was unique, a one-time crossing never to be repeated? What if its anomalies resulted from conditions so rare, so specific, that replication was effectively impossible? Then the data would remain forever unexplained, a footnote in astronomical history, a curiosity discussed in seminar rooms, gradually fading from active research as attention shifted to more tractable questions. In August 2025, a second amateur observation surfaced. A retired engineer in Argentina reviewing personal telescope footage from May 2024 identified a faint streak matching 3i Atlas's trajectory. The images were low resolution, but analysis suggested the object exhibited faint periodic brightness variations, consistent with the 6.7-hour pulsing observed by professional instruments. The engineer published the finding on an amateur astronomy forum. No peer review, no formal verification. Just another data point, independent and corroborating. The observation was noted by professional astronomers, acknowledged as interesting, and filed. It changed no conclusions, it resolved no contradictions, it simply added weight to what was already known. The anomalies were real. By late 2025, discussions had shifted. Less focus on what 3i Atlas was, more focus on what its existence implied. If objects could move through space exhibiting properties that violated known physics, what did that mean for the completeness of current understanding? Were the fundamental equations incorrect or merely incomplete? Did nature permit loopholes, edge cases, rare configurations where normal rules bent? Or was something else at work, something not yet within the scope of physical theory? These questions entered philosophical territory, where data thin and speculation thickens. Science guards its boundary carefully, distinguishing between what is known and what is imagined. The known territory for 3i Atlas remained narrow: observations, measurements, contradictions. The imagined territory sprawled in every direction: exotic physics, undiscovered forces, interactions with dark matter, quantum effects at macroscopic scale. Imagination is useful. It generates hypotheses, but it is not evidence, and evidence in this case ended when the comet left observational range. In the archives, the data persisted: terabytes of images, spectra, and telemetry. Researchers would return to it periodically, re-examining with refined techniques or new theoretical perspectives. Perhaps in 5 years, a breakthrough in plasma physics would illuminate the magnetic field. Perhaps in 10 years, advances in molecular chemistry would explain the sodium inversion. Perhaps in 20 years, a mission to another interstellar comet would reveal commonalities, patterns, explanations, or perhaps not. The universe does not owe us answers. It simply exists, following rules we attempt to decipher through observation and reason. Most of the time, those rules reveal themselves clearly. Gravity pulls, light travels, atoms bond, the patterns hold, predictable and universal. Most of the time. And then, on rare occasions, something passes through that does not fit. An object that moves by its own logic, defying expectations, leaving instruments to record what minds cannot yet explain. Through Atlas joined a small list of such phenomena: unexplained, verified, real. The comet continued outward, beyond Neptune, beyond the Kuiper belt, into the diffuse halo of icy bodies surrounding the solar system. In 300 years, it would cross the termination shock, where the solar wind falters against interstellar pressure. In 1,000 years, it would pass through the inner Oort cloud. In 40,000 years, it would be indistinguishable from the countless other frozen relics drifting between stars, one among billions, silent and dark. But unlike those others, 3i Atlas had been seen, measured, questioned. It had passed close enough to Earth's telescopes to reveal its contradictions, then departed before those contradictions could be resolved. A glimpse into something beyond, current understanding followed by silence. In observatories around the world, astronomers continued their work, monitoring asteroids, tracking comets, cataloguing galaxies. The routine never stops. The sky presents infinite questions, and human curiosity meets them with infinite patience. Answers arrive slowly, sometimes across generations. Newton's laws took decades to gain acceptance. Einstein's corrections took decades more. Perhaps the lessons of 3 Atlas would require similar time, or perhaps they would remain forever on the edge of knowledge, a mystery documented but unresolved, a reminder that observation outpaces theory, that instruments detect phenomena minds have not yet learned to explain. On a clear night in late 2025, if one looked toward the constellation Pisces with a powerful telescope and knew exactly where to point, a faint point of infrared light could still be detected. Temperature, 87 Kelvin. Distance, 48 astronomical units. Velocity, 27.1 kilometers per second. Outbound. No coma, no tail, no anomalies visible, just a frozen rock tumbling through space, indistinguishable from any other. Except for what it once revealed, the data remained. The questions remained. The universe, indifferent to both, continued its motion. Planets orbiting, stars burning, galaxies spinning, and somewhere beyond the reach of human instruments, 3 Atlas moving silently into depths where no telescope will ever follow. What did it mean? What force moved it? What physics governed its impossible trajectory, its inverted tail, its inexplicable magnetism? The answers, if they exist, travel with it. Carried outward at nearly 30 kilometers per second, into the darkness between stars, into the vast archive of things observed but never understood. The laws of motion hold, gravity pulls, light bends, energy conserves. These truths remain, carved into textbooks and encoded in equations. They describe the universe with remarkable precision, predicting eclipses centuries in advance, guiding spacecraft across billions of kilometers, revealing the age and fate of the cosmos itself. But they did not describe 3 Atlas, not fully, not yet, perhaps not ever. And in that gap, between what instruments record and what theories explain, lies the frontier. Not the frontier of space, but the frontier of knowledge itself. The place where observation encounters mystery, where certainty meets doubt, where the known ends and the unknown begins. It is a place humanity has always inhabited. Every generation stands at that edge, pushing forward, illuminating what was dark, explaining what was strange. Progress measures in decades and centuries, each step revealing new landscapes, new questions, new mysteries to replace those finally solved. 3 Atlas became part of that landscape, not an answer, but a question, not a conclusion, but an opening, a small crack in the edifice of understanding, through which something unexpected briefly showed itself before vanishing, beyond reach. What lies beyond that crack? What other phenomena wait in the darkness, following rules not yet written, exhibiting properties not yet named? What will the next interstellar visitor reveal? And will humanity be ready to observe it, measure it, and perhaps finally understand it? The sky offers no hints. The instruments wait in silence. The data accumulates, one observation at a time, building toward conclusions that may arrive tomorrow or may require generations. Until then, the mystery persists, verified, documented, unresolved. 3 Atlas defied 11 laws of comet physics, and somewhere in the cold between stars it continues defying them still, indifferent to human confusion, moving by its own rules, a silent traveller through the dark. The question remains, whose rules? And the universe does not answer.